Alright, let's look at some review questions for your quiz on two-variable statistics. So, we can see that we've got some data that's correlating the length of arm to the time it takes to swim the breaststroke. Here we've got 8 students' data, and we need to calculate the mean and the standard deviation for both x and y. Now I'm just looking ahead for a moment, and I see that I've also got to calculate the correlation coefficient. And so it seems sensible to me that I may as well just enter all of this data directly into the calculator. So let's say stat, I'm going to edit my lists, and I'll create my lists. First of all, my x values, 79, 74, 72, 70, 77, 73, 64, and 69. And in my second column, these are my breaststroke times: 135.1, 135.7, 139.3, 141, 132.8, 137, 152.9, and lastly 144. Alright, let's quit this stat edit screen, and I now want to calculate the mean and standard deviation for each of these variables x and y separately. So let's start with the x. I'm going to go to stat, calc, and I'm going to do one var stats using my values that are inside list 1. And it will tell me that my average x value is 72.25. So my average x value is 72.25 centimeters, right? The length of the arm. And my standard deviation, make sure that you don't read the SX one. We'll always read the little funny symbol, the sigma x. And if I round to 3 significant figures, I see 4.41. But I'm going to try to get into the habit of writing out more decimal places than required. So I've written standard deviation and then a little x below it to show that I'm using the x variable. And I'm just going to write out some extra decimals: 4.40879 ... seconds. That guarantees me full marks, actually, because IB no longer requires it to be exactly 3 sig fig. They just want at least 2 sig fig. I'm now going to round it to 4.41 because I think rounding to 3 significant figures is good practice. But it doesn't matter if you leave too many decimal places in your answer. Let's now do the same thing to y. So we'll press stat, calculate one var stats, but this time we're going to calculate the statistics on list 2, which are all my y values. And I can see that the mean, I know it says mean of x, but the calculator doesn't know that I've called these ones y. So we know that this is actually a y mean is 139.725, which of course we can round to 140 if we were going to go to 3 significant figures. That's seconds, isn't it? I'm just realizing a mistake I've made earlier on. Sorry about this. Even my standard deviation should have been written in centimeters, because that's what we're dealing with for x. So sorry, this was centimeters, this was centimeters. It's my y values that are seconds, aren't they? And my standard deviation is 5.98576. So let's write that in here. So my standard deviation sub y, 5.98576 ... which rounds to 5.99 seconds. There we go, 4 easy points. Part B, calculate the correlation coefficient R. Alright, so we'll press stat, calc. Oh, I forgot, I haven't turned on my diagnostic. So let me quit. Now if you've got a new operating system, you can just press mode and go upwards, and you'll find that they're easy to turn on your stat diagnostics here. Go to on. Done. And now I can quit. Those of you that don't see that menu will have to press second 0 to enter the catalog, you're going to have to scroll down to option D, and why haven't I managed to go to option D? Oh, I've gone too far, sorry. Option D. There we go. And I'll scroll down to diagnostic, on. Okay, diagnostic on, enter. And that accomplishes the same thing. Either way, my stat diagnostic is now on, so now I'm ready to do a linreg, so stat calculate linreg. And I want to do a linreg. Now I could say on list 1, comma, list 2, because these are my x values, comma, these are my y values. I could actually leave those out because when your x values are in list 1 and when your y values are in list 2, it's not really necessary to say this. The calculator assumes that your x values are in list 1 and your y values are in list 2, and if they are, then you actually don't need to include these parameters. You can just say linreg and nothing else. At any rate, we can see our equation of the regression line, so I can actually answer part D straight away, that y is equal to ax, so a is negative 1.27684. Let me just immediately round to 3 sig fig. 1.28x, and plus b, and b is 231.9, which rounds to 232. And I'm supposed to, I jumped ahead, didn't I? I was supposed to calculate the correlation coefficient, which I can now see is negative 0.940. So r is negative 0.940 when I round to 3 sig fig. And I need to comment on my value for r, and I can see that it is a strong negative correlation, because my r value is very close to negative 1. That's what makes it negative, and because it's so close to negative 1, that's why it's strong negative. And part E, using my regression line, I should estimate how many seconds it will take a student with an arm length of 75 centimeters to swim the 200-meter breaststroke. And so their length of their arm is now 75 centimeters, so the x value is 75, so let's substitute 75 into this equation. And so our y value is going to equal negative 1.28 times my 75. I should have probably written that down here. So the y value, the swimming time that I'm looking for, is negative 1.28 times 75 plus 232. And that gives me times 75 plus 232. And that gives me 136. And that seconds will be their time in the breaststroke. Number 2. So the local park is used for walking dogs. The sizes of dogs are observed, so this is our matrix of observed values. And the numbers of dogs present classified by size at 3 different times. So these are the different times of day. And this one, small, medium, large, that's obviously size of dog. Okay? So we need to write a suitable null hypothesis. So the null hypothesis is that this category, time of day, is independent from this category, size of dog. That would mean then that it doesn't matter what the time of day is. There's nothing that would give us any indication that some sizes of dogs are more liable to be out at certain times of day, or vice versa, that it will be a certain time of day when we see a particular size of dog. So a null hypothesis is the one that says that these are independent factors. The null hypothesis is denoted as h sub 0, and our statement here is going to be that size of dog and time of day are independent. And then we've got a choice of words here. We can use factors, or you can use variables, or you can use classifications, whatever. Any of those 3 words will do. Part B, write down the value of chi-squared for this data. So let's create a matrix. Edit. I need to create a 3 by 3 matrix. And I'll put in my values. 9, 18, and 2. 11, 6, and 13. 7, 8, and 9. Alright, once you've entered in your last value, let's quit. And now we'll perform a chi-squared test. We'll say stat tests and go up to option C. That's the chi-squared test. And we're going to do a chi-squared test on, yes, our observed matrix is indeed matrix A. So let's go straight down to calculate, and our value of chi-squared I can see is 14.899. Well, that's close enough to 14.9, isn't it? So chi-squared equals 14.9. The number of degrees of freedom is 4. Show how this value is calculated. Alright, so let's look at the number of rows. We know that in general, your degrees of freedom is rows minus 1, so I've got 3 rows minus 1, and I've got 3 columns minus 1. That's going to be 2 times 2, and therefore I get 4. The critical value, they tell us, is 9.488. Well, that's nice, because when they give us the critical value, which we normally call k, we can compare our chi-squared to the critical value. If chi-squared is less than the critical value, then we have independent, so we keep HO. If chi-squared is greater than the critical value, then they are dependent situations, and we keep H1, the alternative hypothesis, and we reject HO. So let's look at our situation. If we compare our chi-squared value to the critical value, we discover that because 14.9 is greater than 9.488, meaning that my chi-squared is greater than k, this must mean that I have a dependent situation. I must reject my null hypothesis. So what conclusion can be drawn? We will reject the null hypothesis since chi-squared is greater than the critical value. So let's just put this back into context now. This means that we can conclude that the time of day that a dog has walked and the size of the dog, in fact, surprisingly maybe, are dependent factors. In fact, there is some impact, and trying to think about why this might be. I mean, I wonder whether particular dog owners who have particular sizes of dogs would be more available to walk them at certain times of day. It might be that bigger dogs need to go for walks more often to you know what. So we can say then that therefore size of dog and time of day are dependent factors. Alright? Let's go on to number 3. The sketches below represent scatter diagrams for the way in which variables x, y, and z change over time in a given chemical experiment. They're labeled 1, 2, and 3 for our x, y, and z. Alright. Which of the diagrams indicate that the pair of variables is not correlated? Well, here we've obviously got a pretty strong negative correlation. This one looks like a fairly weak, but still I can see sort of a pattern to the x's, that they seem to be coming downwards. So that's going to be weak negative correlation. Here I can't really see any pattern. I see no indication whether this is positive, negative, or nothing. So I think we're going to say that diagram 1 is not correlated. And shows strong linear correlation, that's going to be diagram 3. A student is given a piece of paper with 5 numbers written on it. She is told that 3 of these numbers are the product moment correlation coefficients for the 3 pairs of variables shown above. So let's have a look at those 5 numbers. So for each sketch above, state which of these 5 numbers is the most appropriate value for the correlation coefficient. Okay, well we said that this first one had no correlation, so which of these 5 numbers indicates no correlation? It's going to be the one closest to 0, doesn't it? This one is of course stupid. This one can't even exist. How can you have a correlation coefficient greater than 1? So what, it fits the line more than 100%? Well, that's silly. This is the strong negative one, isn't it? So this one's going to be diagram 3. This one is almost no correlation, so that's diagram 1. So for 1, it's 0.04. For diagram 3, the strong negative, that's going to be negative 0.85. And then it looks like I have a slightly weak but negative correlation there. I guess that one's the negative 0.20. Alright. For the 2 remaining numbers, state why you reject them for this experiment. Alright, well I already talked about reject 1.60. Since negative 1 and r must be in between negative 1 and positive 1, and I rejected 0.9 since we have no positive correlation here. Okay, since none of the scatter plots indicate positive correlation. And maybe I want to be really thorough and I just say they are falling. I don't know. They are falling with negative slope. Gosh, I don't know. Maybe I'm saying too much. Negative slope. Well, it doesn't hurt to be thorough, right? Oh gosh, we're done that question. Let's do number 4. Alright, we've got the cost in Australian dollars of 7 paperback books chosen at random, together with the number of pages in each book. Now, these are simply the numbers of the books, so don't get fooled. We're not going to put this row into our calculator in any way. We're comparing variable x to variable y. This is just numbering the 7 books. Don't even worry about it. So we need to plot these pairs of values on a scatter diagram. Use a scale of 1 centimeter to... Alright, so I guess I better see if I can find any IB graph paper. And, gosh, how am I going to draw on this? Thinking. Yes, sorry guys, just trying to work out what I'm going to do here. I have an idea. Maybe I can annotate on this, something like that. So I need to then draw a scatter plot. Sorry, I really should use a ruler, shouldn't I? Gosh, it's so easy in my software, I may as well. So, let's think. I need a vertical line. Let me move it over a bit so that I can label it. And now I need a horizontal line. Oh, sorry. Need to choose horizontal line. Okay. Thinking. What am I going to do here? Maybe I can snip. Alright, I'm done. So maybe I can... Oh, that didn't work. Golly, how am I going to do this? You might just have to draw the scatter plot on your own, I'm afraid, or accept a very rough sketch on my part, because I haven't really figured out how I'm going to get. Yeah, see, it's not even allowing me to. I'll fool around with this for 1 minute, but I don't want to waste your time as you're watching this video. Alright, there it is. so never mind. Let's just get out of here and go back into the Word document, and I'm just going to have to draw you a very rough scatter plot, sorry. So let's make sure that we set up 1 centimeter for each 50. 1 centimeter on the IB graph paper is 5 of the little squares. Okay? So that's, 1 centimeter is 50 pages on the horizontal axis, and then 1 centimeter is 1 Australian dollar on the vertical axis. Okay, so I've got to come all the way up to about 8 centimeters. 1, 2, 3, 4, 5, I'm going to cheat. 1, 2, 3, 4, 5, 6, 7, 8. There we go. That's 8. And 1 centimeter, is 50 pages on the horizontal axis. I've got to go out all the way to 630 pages. So 50, 100, 150, 200, 250, 300, 350, 400, 450, 500, 550, 600, and I guess I've just got to go up to 650. Let's put in the values. So we've got 50 is 6, so that's 4, so the 50 is 6. And then 120 pages is 5.40. About there maybe. And then 200 is 7.20. And then 330 is 4.60. 400 is 7.6. 450 is 5.8. And 630 is 5.2. Okay. Alright, we have to write down the linear correlation coefficient R. So it looks like maybe I've got some slightly, some moderate negative correlation. It does look like it might be falling ever so slightly. So let's find out what the strength of this correlation is. So I better enter these as my new list. So in stat, let's clear the old lists. We'll just move up to when list 2 is highlighted, and we'll press clear, enter, and we'll go over to list 1 and select list 1, clear, enter. Alright, and here we go. Our X values are 50, 120, 200, 330, 400, 450, and 630. My list 2 values, 6, 5.4, 7.2, 4.6, 7.6, 5.8, and 5.2. And now I'll press Stat, Calc, LinReg, and because my diagnostic is already turned on, and because list 1 is my X values and list 2 is my Y values, I can see my R is negative 0.208. R is negative 0.208. So it's kind of what I said, right? Slightly negative, but not very strong correlation at all, it appears. That's such a low R value, fairly close to 0, so very weak negative correlation. Part C. Stephen wishes to buy a paperback book which has 350 pages in it. He plans to draw a line of best fit to determine the price. State whether or not this is an appropriate method in this case, and justify your answer. This is a very tricky question, because there's two things that you need to consider when you are thinking about whether a line of best fit is an appropriate method. The first thing you need to think about is interpolation versus extrapolation. Interpolation means that we have chosen a value that does fit inside my minimum number of pages and my maximum number of pages. 350 is well within this set of data. Interpolation is good. So this is a nice situation. What if it had said 1,350? Now 1,350 pages is so far outside our range of data, which finishes at 630, that's called extrapolating. That's not a good situation.